Right. So I work at Yandex Zen. That is an algorithmic newsfeed, and this is actually the title of my talk today. And there I'm senior machine learning engineer. So I do all that data processing. I also train machine learning models and stuff. So I pretty much know everything about that system, and I will share some insights with you today. So this is how it looks. So Yandex Zen is actually an infinite feed that you can scroll, and it gets populated with more and more pages from the internet that you might be interested in. And our ultimate goal is to bring that interesting content from the internet, no matter what. It might be a forum post, it might be a video, or it might be just a news article from CNN. So it may be anything. I want to show you some numbers so that you appreciate the scale of the service that we have right now. We have 10 million daily active users. We have 40 million monthly active users. And our users, on average, spend around 40 minutes of their day just reading the stuff that we got there for them. And the most interesting number is how much time we got to produce those recommendations, and we just have half a second for that. It is pretty big number, by the way. So, but a lot needs to be done in those half a second, and we will talk about that and how to do that quick. So that's it. And actually, essentially, Yandex Zen is just a recommender system. So we have a user with a browsing history, so we know something about her preferences already. We have millions of web pages that we just crawled with our spider. And in the center, we've got a recommender system that tries to give the user the most interesting pages from the web. And what we want to do, we want the user to be happy, right? So the ultimate goal is for user to be happy with the system. How to measure that happiness? So that is a difficult question, but we measure different stuff. We measure how many clicks you do, how many sessions a day you have, how much time you spend with our service, and how much likes you give to our service. So we measure all of that. An interesting fact is that you see here we have a user with a browsing history, but that is not always the case. Sometimes a user doesn't have a browsing history. Imagine that a user comes to our service for the first time. We've never seen her before. But we still know something. Because Yandex is a search giant in Russia, it's actually more popular than Google. A lot of people use it. And a lot of sites in Russia have a piece of JavaScript that just tracks the users so that we can provide them with great advertisement, right? But we can use the very same data to produce something, I don't know, something more meaningful to those users. So if we have a user that comes to Yandex Zen for the first time, we still know something about her. We still know the pages that she visited before, because that very same information is used for ads. So, but if we don't have that, it might happen that we have a user and we know nothing about her. Then we have an onboarding process, as we call it. So we ask a few questions so that just to know, I don't know, your main interests, what domains are interesting to you. It looks like this. So we need that to jumpstart our recommendations, because otherwise we know nothing and we can show you just most popular items, and that doesn't work. So people need some personalization. And this is how our onboarding screen looks like. It's pretty easy, it's suboptimal, but that is what we have now. So we have the most popular topics inside Zen. It's like technology, news, politics, sports, and so on. And from those topics, we have the most popular domains or sites, right? Like if it's technology, it could be Engadget, Gizmodo, Gizmodo, right, or The Verge, or any other site. And what we ask you to do, if we use that, if you use Zen for the first time, we want you to pick 3. So we have a lot of categories, we have popular domains from those categories, and you just need to do 3 clicks so that we know something about you. And we exploit that information heavily to show you something relevant so that you start using the service, you give us feedback, and we learn on that feedback. So let's say that that process is over. So you started using the service, you click some items, you don't click other items, and we use that information to personalize the service for you. So let's say that a user already has a browsing history. So let's look at that case. What we're interested really in this talk is how to do that recommender system. So what techniques and what algorithms can be applied here. Basically, a recommender system tries to solve this problem. It's called ranking problem. Imagine that we have millions of pages from the internet, but we need to select only 20, the most suited for you, right? So we need to do that somehow. And this is essentially the problem of recommender systems. And before I proceed with the technology that we use inside, I want to remind you about some classical algorithms that are already out there and that algorithms that anybody can use, so that we would be on the same page and I can share you some insights that we have. So who of you is, is familiar with matrix factorizations, so that I just know that? Oh my God, so a lot of people. But still, we need some, some basic information so that everyone can grasp this talk. Okay, so what do we have? Imagine that we have an explicit feedback. Explicit feedback means that the user says us that I like this item and I dislike this item. So this is explicit. And if you take internet, like movies database, imdb.com, right? You can give stars to the movies. And maybe IMDb can produce recommendations for you based on those stars. And actually giving a star to the movie is an explicit feedback. If you give 10 stars, then it's a great movie. If you give 1 star, then that movie sucks for you, right? So imagine that we have this huge matrix of ratings. We have a lot of users, we have a lot of movies, and some of these cells in this matrix are filled with the rating that the user gave to the movie. We need to populate those missing ratings, because those missing ratings will actually produce recommendations for the user. So what do? We want to approximate these metrics with the product of a much smaller matrices, which are in yellow on the slide. And the trick here is that M and N measure like in millions, okay? So we might have millions of movies and millions of users. But K there might be very small, like 100. And if K is small, it makes sense because it actually helps us to understand the underlying interactions of users and items. And we actually try to model that interaction with a dot product. So if you imagine that we have this rating 5, we need to predict it somehow. And what we do is we have a different vector for each user, and vector is just a bunch of numbers, like let's say 100 numbers. We call it a vector. And we have a vector for each movie. And this model tries to explain these ratings that we see with a dot product of those two red vectors. And the dot product essentially says us how much those vectors are similar, like in 100-dimensional space, whether they point at the same direction. So we try to find such vectors that we explain all of these ratings. So if we dive a little bit in the math, we have this objective for our optimization problem. So we just want to predict each rating that we have here with a dot product of user vector and item vector. And our loss function here is just a squared loss. So it's just a squared error. And we need to minimize it somehow, right? So we need to find those values for matrix P and matrix Q. We need all of them. So where do we get them? You can use pretty much any optimization algorithm here. But the one that we like is called alternating least squares. You can use it for explicit feedback, and the idea is the following. If you look at this objective, you can actually see that if you fix, for example, matrix P, then whatever is left of your objective is actually a linear regression. So if P is fixed, it means it's constant, right? We don't need to minimize over P because it's already known, and whatever is left is minimization over Q, right? So if you look at this, it's actually, we need to find a vector of weights so that we multiply that by our features and we predict the ratings. So it's like, it's classical linear regression. And if we go into like less technical detail, this is how it looks like. Imagine that we have users 1, 2, 3, and imagine that we already have the vectors for them. It's vector 1, 2, and 3 respectively. So these ones. And we already know them, like we got them somewhere. And imagine that right now we need to find a vector, the most suitable vector for our item, this one. So, and what does it mean, the most suitable? We want to approximate the ratings that we see here, right? Like 5, 1, and 4. We need to explain those ratings. So we need such a vector for our item that if you take a dot product with the first user, it will yield 5, or approximately 5, like 4.5 is also okay, right? And this is essentially a regression problem. And regression problem is an easy problem. It's a linear regression, you can solve it instantaneously. And that's what we do. Let's say that Q and P are populated with random numbers, like random, right? We fix P, we find the optimal Q, solving linear regression, and that, what do we do then? You see, it says alternating. That means that we need to do different steps here. And what we do next is we fix item vectors and do the same for the user vectors. So that means that we try to solve this optimization problem in such a way that on each step we fix user vectors and optimize for the items, and then we fix item vectors, Q, and optimize for the users. You can see that it is a kind of symmetrical thing, so it doesn't really matter whether you fix Q or P, you solve regression. It's still a simple linear regression. Okay, so
does it guarantee the optimal or suboptimal?
Yeah, you know, it will be optimal. The convergence, I'm not sure that like there is a theorem about convergence of this thing, but in practice it converges, so everything is fine. Okay, what's next? I want to give you, some explanation on the with my hands, like waving my hands and saying like how it really works. So that vector that we have for each user and for each item is actually a bunch of numbers, right? But what do that numbers mean? So where they come from? Imagine that we have movies, and we have two characteristics of those movies, whether it's fictitious and whether it's funny, right? So we have the axis for comedy and we have the axis for fiction. And if we say some movie, for example, Thor, right? It might have two numbers, those two characteristics. So comedy is 0.8, so it's pretty much a comedy, right? And it's, it's an average on the fiction, right? So there are more fictitious movies. So we have that vector, we also call that embedding vector, because what we actually did here is we took a movie, which is like it's video file, right? It's pretty complex. And we got from that movie to two numbers. And we call it embedding because we actually came to some other space or dimension, yeah, where you describe it with two simple characteristics. Okay, so let's take another movie. And let's say that we have a specially educated person who can give those numbers to the movies. And he comes through the list of all the movies and gives us all the numbers. What can we do next? We can actually compare those movies. For example, there's another movie, it's called Dumb and Dumber. And it's pretty much a comedy, right? And it's not that fictitious. So it can happen in real life, right? It happens. So if you have those vectors, you can actually measure similarity of them. You can measure like how much are we confident that they point in the same direction? And if they point in the same direction, that means that their characteristics are similar, right? So to compute that similarity, we actually take a dot product. So a dot product is the following thing. You take two vectors, you multiply them element-wise, right? And then all that numbers that you got, you just sum them up. So just a sum of element-wise multiplications. And there is some geometrical explanation why it actually measures the similarity of vectors. Okay, but the if I tried to explain a dot product in simple words, it would be the following way. Imagine that we have those vectors, and imagine that they have the same length. Then a dot product actually shows you how big is the angle between those vectors. If it's small, then a dot product will be big. So that's it. All we care about here is the angle. Okay, so if we have these vectors for all our movies, then you can actually see that like the smallest angle here is between Thor and Dumb and Dumber, right? So that means that these movies are the most similar. So they are the most similar. Okay, so why do I show you this image? Because we will actually use this idea that all movies are in some space of characteristics, and we can compare movies based on that characteristics. So, remember that idea, okay? And now we have the user. Imagine that the user comes to our image and says, okay, I like this movie, I like that movie, but I hate Thor. Okay, we need to infer something from this information. We need to know what this user basically likes. So what do you think? Where the vector for the user points? So where does it point? Where will it go? It will go up, down, to the left, to the right. Down. It will go down, right? It's like, it's trivial. Like it's, I don't know. So everybody answered correctly. And yeah, it goes down. Why it goes down? Because it's similar to the items she likes, okay? So the angle here is small and the angle here is small as well. So it's close to the movies she likes and it's far away from Thor, which she hates, right? And it turns out that if you want to code that logic, you actually come to the ALS algorithm that we have overviewed. It does the very same thing. It says that for the items that I like, I will have a big dot product, otherwise it should be small. Why do we need that vector? Why do we need that red vector? What do you think? What do we do with that? Yes, we use that for future recommendations, exactly. So because we have all the other items here, they're somewhere here and they have their own vector. So let's just compute the similarity, right? Let's just compute the angle between new movies for that user. And our recommendation engine can produce a movie which is somewhat similar to the movie that the user also likes, like it's Schindler's List, for example. So we use that information, right? We use those vectors to produce new recommendations, and ALS gives us those vectors. The idea that we remember is that we have those characteristics, right? But we actually don't need people to annotate those characteristics because algorithm can find them for us, right? They're called latent variables. We don't know what that characteristics actually mean, but they're useful for this algorithm and they're useful for producing new recommendations. So we don't know whether it's comedy or fiction, it's just some numbers, but the idea is the same. Okay, a little bit more math, okay. There is also a different type of feedback, and we really need to take that into account. There is implicit feedback. That means that we only have one type of feedback from you. You say, I like this item, and this item, and that's it. You never say us what you dislike, and that makes the feedback implicit. And that means that we need to solve this problem a little bit differently. And we have this problem when we have a new user which only have external page views. Because if you have external history of the user, like what page views she visited, then you don't know what pages she doesn't like, right? So you have only one kind of feedback, and that is a problem. The basic idea is to do the following thing. Let's say that if she visited it, if she visited that page like 2 times or 3 times, let's say that she likes that item. And we will say that that is a pure preference, right? So she prefers that item. But we also have a different component here. We also have this so-called confidence. So we have preference, whether she likes it or not, but the confidence is proportional to how many times she visited that page. So if she visited many times, then we are more confident that this preference is like real, right? So what we do next, we have this optimization problem. You can actually look it up if you search for IALS for implicit feedback. You can Google it easily. And what it actually does, it tries to predict a preference with a dot product with the weights of that confidence. The basic difference from explicit feedback is that for all the pages that you haven't visited, we try to predict 0. We try to predict 0 preference, but with a small confidence. And this is a trick here. So if you imagine that you learn a classifier, like you have a machine learning problem, and you have the examples of only one class, how do you train it? You need some examples of a negative class, right? So that you can discriminate between them. But if you don't have them, then you have a random sample and say, okay, these random samples will be the negative class, and I will just distinguish between those classes. I will like train a classifier that will say whether it's a cat or a dog, for example. So, and the basic thing is that it can be solved very efficiently. So that is all the formulas that we actually need. And now I will tell you what we actually use at Yandex Zen. First, when the user comes and he has only external page views, right? That feedback is implicit, as we now know. And so if we want to use that feedback, we actually need to use implicit ALS. And what we do here, we also aggregate that information down to the publishers. For example, if you read like an article from CNN, we say that, okay, we forget about that article. It's just CNN.com, okay? It's just a publisher. So we do that to reduce the dimension of the data, but that is really the only place we reduce that information. So we have a matrix which has users and publishers and have some ratings, whether they visited that publisher or not. So what happens next? What do you think happens next? So we have these metrics. Why do we need that? Yeah, we train that implicit ALS, and it gives us what?
How much you use the like publishers?
Yeah, it gives us predictions for the new publishers. So based on what you like to read, like CNN or something like that, we can actually find something similar to CNN. And we can take items from that similar publishers. And that is what we actually do. So we take predictions made by implicit ALS. We take those new publishers that you have never seen, but they're pretty similar to what you read. And we take the most trending items from those publishers. This is a heuristic. It doesn't work that well, but that is still used today as one of the features. So I'm telling you about that. And what we actually done here is we produced some candidates for our ranking. Imagine that we have millions of pages, right? You can't score all millions because you just don't have enough time. You have to select, like, roughly the items that are more probable to be the answer in our recommendation system, right? Our result that we show to the user. And we want to strip off all the items that are non-relevant. This is rough estimation of that ranking, but still we need to do that because otherwise we wouldn't fit into those 500 milliseconds. So we have these 1,000 pages, and then we can apply, like, I don't know, complex machine learning algorithms that will rank those 1,000 to get the top 20. So how do we do that? How do we go from 1,000 to 20? We actually need some features, right? Like in any machine learning problem, you need some features. Then you use gradient boosting, and we have our own flavor of gradient boosting. It's called cat boost. If you haven't heard about that, just Google for it. Then, when we use that formula in production, we actually have some feedback from the user. She actually likes some items or dislikes some items. And it goes back to the features because they use that information as well. They train on that information, they aggregate that information. So there is a constant feedback loop here. Okay, so what features can we calculate here? First, the most obvious choice are user features. Based on what you've visited on the web, we can pretty much, we can predict with a good quality your age, education, and income, and stuff like that. Because that information is very valuable for advertisement. So that's why we have good classifiers for that. There are a lot of different classifiers, but all of that is just information about the user, you see? It doesn't take into account the items she likes. Then we have item features. What item features we might have? The obvious one is popularity. If the item is popular with majority of the users, then it is most likely that our user will like this item too, right? Another thing is a little bit more sophisticated. We try to predict the lifetime of an item. Imagine that there is a web page. We need to know for how much longer it will be visited by the users. We need to know that, it's not a one-day new, not a one-day news article that will go away, right? We need to know that beforehand so that we can use that information and show that before it dies. We can also predict a lot of stuff based on the text and the image that you have on your page. We use a lot of deep learning there. I will talk about that a little bit later. You can, for example, predict whether it's an article about sports or about politics, and that makes sense. We need to distinguish those things because it will help to produce greater recommendations for the user. And last but not least, actually our best features are here. They are about user-item interactions. So we need to know that we need to have some features that actually take into account the user and the item and try to estimate their similarity. And here, of course, we use matrix factorizations and neural networks because everybody today uses neural networks, right? So why not? So the first thing that I want to tell you is what matrix factorization we use. This time we use a much bigger matrix of ratings. We have 20 million of users in that matrix. It is actually a sample of our data. And we have 2 million of items. So it's like a big Excel sheet, right? Then we have 70 billion of ratings in that matrix. It is filled with 70 billion of them. What are those ratings? It has 1 if there was a click, and it has 0 if there was no click. If we showed you something but you didn't click it, so that means that most likely you didn't like it, right? So we think it's a kind of an explicit feedback. If we showed you something and you refuse to click it, then it's not so good. What do we do next? If we try to find a vector for each user and for each item of length, let's say 100, that means that those two small matrices don't occupy much memory. If you think about it, they actually occupy just 8 gigs and 1 gig of RAM respectively. So you need 8 gigs for this matrix, like 20 million by 100, and you need only 1 gigabyte for that matrix. So they're pretty small. That means that we can scale it efficiently. We can scale it without problems because that becomes an embarrassingly parallel problem. What we do is we just take 1,000 computers, each of them try to solve the problem for the user. Let's say this is a ratings matrix, and these are the ratings of a user, let's say X1, right? And if we need to find a perfect vector for that user, we need the vectors for these 2 items. And we don't use sophisticated technique how to sync those vectors, we just broadcast them. Because they occupy just 8 or 1 gig, it's not that much. We can just send them over the network to each machine. And then we can use that updated vectors to do embarrassingly parallel ALS steps. On each node, we can solve the problem for, let's say, a bunch of users. Because these problems, if you think about them, they are independent. So that's why it's embarrassingly parallel. It takes just 12 hours to train that huge matrix factorization on MapReduce with 1,000 CPUs. So this is one of the features that we use to rank 1,000 candidates for our gradient boosting formula. There are some problems, though, that we had to overcome so that this factorization is actually usable in production. The first problem is how to handle novel items. Imagine that we update this factorization every 12 hours. There might be a problem because if like a news article appears and we didn't have it in that factorization, that means that we don't have a vector for that item. That's a problem. So we actually decided to update those vectors more frequently. You can actually do the following thing. First, if a new item appears, you don't know anything about that item. That means that you have to do exploration either way. You have to show that item randomly to random users just to collect some feedback, whether they like that item or not. Then, when you had some ratings from exploration, what can you do? You can actually update the vector for that item. If you remember how alternating least squares works, it actually takes the user vectors, which are fixed, and tries to solve a linear regression, right? So it tries to find this vector as a solution of a regression problem. That means that if you take the users, which we had 12 hours ago, and these are pretty much the same users, we can actually update with the new ratings that we got from that last hour for the item, we can update this vector for them. So that's why it's like usable, because if a new item appears, we need just 1 hour to collect the ratings and to update the vector for that item. So what do we do for new users? What do you think? Like a new user appears, like types in Zen Yandex.com, yeah, and so we don't have vector for that user. What do? We do the same thing, actually.
Fix items.
Yeah, we fix items, right, and we try to solve the regression problem for that user. So we store all item vectors in runtime memory, and they occupy just 1 GB. Remember, it's not that much. But we don't need to store all user vectors because it's cheaper. I mean, it's easier to compute them. It's easier to compute them at runtime. And what we need to do is we need to do an ALS step, probably the same ALS step, but imagine that here we have items and here we try to find the vector for the user. It's like a symmetrical problem, really. So you can fix either users or items and you can do this trick. So it's easier to compute them, and we do that. And we do that in a highly optimized code. We actually use some vectorized instructions on modern CPUs that can do that pretty fast. So we can do that like in 10 milliseconds, and boom, you have a vector for the user. So if a new user comes to our service and tries and then gives us some feedback, like I like this item, oh, I don't like this item, then in the next request to our service, we can actually update the vector for that user and provide like the freshest recommendations for that user, taking into account all the history that you already have. So that we always have an up-to-date vector for that user. Okay. That is a pretty classical algorithm. Like ALS have been invented like, I don't know, 10 or 20 years ago. So it's pretty old, but it's still usable and it's still scalable. So we can also use neural networks. And the first neural network that I want to show you is called DSSM. Have you heard about that? Anybody? Okay, there is one. Like DSSM stands for Deep Semantic Similarity Model. I don't know. And basically it's just a neural network that tries to do the following thing. We have some user features, like, I don't know, his age, education, what items he likes or dislikes. And we also have item features, like, let's say, the category of the item, the length of the item, how many pictures it has, and so forth. Then we use some neural network magic, like some layers of the deep network, and then we try to predict the user vector and the item vector. And we try to predict the click. We actually need click prediction. We need to predict whether the dot product of these two vectors will yield a click or not. So whether the user likes that item or not. So what item features we can get? We can actually take a bag of words of all, of item text. We take all the words from there and we use a simple bag of words representation. We also use image embedding that we got from an ImageNet network, like everybody does it that way, right? And we also have some user features. We can take like liked or disliked publishers. We can take bag of words of clicked or non-clicked items, item texts, and we can use that as well. All our features that we have, like all the best features that we have, they all share the same characteristic, and I will ask you about that characteristic in a minute, but I hope that you will spot it on the slides. So we have item vector and user vector, and we try to predict the similarity with the dot product. That means that we need that item vectors in memory. Why do we need them in memory? So that we can calculate that for new items, right? So the new items that the user haven't seen. We need that in memory. And what about this thing? What do we do with this thing? User vector. Unfortunately, we have to do that offline because neural networks are pretty slow. You either need a GPU or a small network, so do that offline. We just do that offline and put those vectors into a key value storage, and that's just all right. So the vector is a little bit outdated, but that's fine. The last feature that I want to present to you is a pretty simple one. It is still based on neural networks. It used the model called BERT. Have you heard about that? Yes, good. So we use that to produce item text embeddings. We just want to take the text of the item, like pass it through a special neural network, and that network gives us a vector for that item. What do we do with that vector? What do you think? Why do we need that? Yeah, because it somehow encodes the similarity of the items in a sense that items that have similar texts will also have a similar vector, right? We can use that. And how do we use that? We make an ALS step for the user. We just take the items, we fix them with these BERT embeddings, and we solve this regression for the user. And that's it. It's like the basic technology that we use. Right. So the thing that I wanted you to spot is that all our prominent features actually share the same characteristic. And it is the fact that every new feature is based on yet another embedding. So you actually need to think about items as vectors because all these features do that. So for example, this feature has a vector for the user and for the item, right? This one also has it, but that vector is computed with sophisticated deep neural network. This one does just pretty much the same thing. So BERT is just a neural network that produces that vector. So that means the following thing, that we can compute a lot of these features in runtime. So for example, we can take 1,000 items that are most suitable for you, and we can compute each feature for each of those 1,000 of items, right? Because it's pretty easy to do a dot product. It's an easy operation, and you can actually make it a little bit quicker if you do that with vectorized instructions on CPU. So we can do that in thousands. So that is pretty much it. That's how it. That's why it is fast, and these are the features that we actually use. Actually, recently we found like one more thing, you know. And we actually found that if you calculate your features as a dot product, you can actually employ some sophisticated vector indexing so that you can find the most similar vectors for the user in sublinear time. That means that you don't need to go through millions of vectors. You just use some special algorithm, which is called HNSW. You can actually Google it, and it's pretty good. And that means that if you have millions of vectors, you can find the most similar for our user in terms of dot product, in terms of that similarity of the vectors. And it is done in sublinear time, which means it is faster than just calculating naively all those dot products. And this is actually like the star of the dish, if you say so. Like the fast approximation of nearest neighbors is a pretty good thing. So that means that we can select that 1000 not based on that simple heuristic that we've started this talk, but with like better features, with that matrix factorization or neural networks or whatnot. So what are the takeaways of this talk? If you start building a recommender system, you shouldn't omit classical algorithms because they still work, you know? Like an ALS is a pretty classical algorithm, yet it is scalable and it is useful in production. What else? You need to think about your items as vectors. It is a pretty, you know, it's a novel concept that comes from deep learning, but you actually should think about that. Like that everything must have an embedding, must have a vector of some numbers that in some latent space describe our item. So think about items as embeddings, because that gives you some good things, like you can utilize neural networks to get more of those embeddings, because there are all sorts of networks and loss functions that can give you more and more of those item embeddings. And the last but not least is that you can employ that smart indexing for approximate k nearest neighbor search, and it is done in sublinear time, and it enhances recommender system very greatly. So I believe that's it. Thank you for listening. And I'm ready to answer your
So for each item, you can represent it with multiple vectors. The question is, how do you represent all these vectors? Do you take all these vectors and create a matrix? Or instead you take all the vectors and create a single vector that will represent your item eventually?
Okay, I got it. We try to take that similarity for each embedding as a dot product as just one number, right? So imagine we have one vector, like from like DSSM, for example. We take a dot product of user vector with each item vector, and we just have a scalar, right? And we put that scalar in our features matrix that we have there, right? And it's just another feature for gradient boosting. So this is the way it works today, guys. So you just add a feature to gradient boosting, you train gradient boosting trees with like tens of thousands of trees, and it just works, right? So you don't need to think about how do I combine them, right? The gradient boosting will do that for you. You just train like independent features and throw gradient boosting on top of that, and it just works. Yeah. Yeah, one more.
Question regarding the network. Can you use just let's say concatenate the features and use just feed-forward network and
Yeah.
Yeah.
Of course you can. So I'll repeat the question. Why don't we take all those vectors, concatenate them into a big vector, right? And then make it smaller with a neural network. Why don't we do that? Because gradient boosting works better, that's why. And we don't want to apply neural networks in runtime, because they're pretty slow, you need a GPU for that, right? So, yeah.
The question was instead of DSSM,
Yeah.
just,
Instead of DSSM, let's go there. Yeah.
just to concatenate user features and item features, and,
Yeah.
and to use the regular features.
Yeah, very good question. Why do we do a dot product here? Because dot products are fast, and you can calculate like 1,000 of them in just a millisecond. That's why. We just want that to be fast. This is the first point. And the next point is that we can use that HNSW algorithm that will give us the approximate like top dot products for the user. If you use a neural network with a feed-forward like layer, like feed-forward network, right? To use those embeddings to produce that final prediction, then you can't use that algorithm. That's the point. Yeah, very good question, by the way. Yeah.
Hi. So for the cold start problem,
Yeah.
on the user side, except for the user to publisher, do you go to a lower granularity than?
Yeah. Yeah. So you've actually spotted our, I don't know, weakest point, I believe. So right now we invest a lot of time into that problem. We finally decided that we don't need to aggregate down to publishers because we now have better algorithms. So we can go to the pages level, right? We can take user to publication metrics of those implicit feedback. So each user has some page views from the history, and they are implicit. So we know only like good clicks. We don't know bad clicks, right? And we will train just IALS with the same MapReduce code, and we will use that pretty soon. So that is a good question as well. Yes, that is a weak spot. Okay.
But then you get very sparse data, right? Like extremely sparse. So
yes.
I don't know, how do you handle that?
Okay, so surprisingly, these ALS algorithm still works. So the sparsity is very high. For example, if you have a matrix like 20 million by 2 million, right? That means that how many cells do you have in that matrix? It's like 40 what? Like 10 to the 12th, I don't know the name for that number, right? It's really big. But if you look at like the cells that have non-missing values, you have only 70 billion, right? And billion is 10 to the 9th. That means that you're missing like 3 zeros. That means that the sparsity is roughly 0.001, sorry, 0.001, right? So most of the cells are missing. But still it somehow works, right? And that is that is basically, I don't know, for any recommendation system it is true, I believe. So most of the rating matrices are really sparse. But thanks to the fact that in ALS algorithm, for example, we only care for non-missing values, and we have regularization here. So if we go into more machine learning techy stuff, we also have this one, right? And it tries to regularize our problem so that we don't overfeed that much, and somehow that helps. That helps to.
You optimize for CTR and you also classify pages, but those are kind of prone to overfeed objectively. Do you use any engagement metrics to support regions, TTR, whatever, something that has some more implicit but then more aggregate data stuff to prevent just a click and a bounce?
This is probably the best question because it is like the root of all evil, that clickbait. Like, oh, father, tell me, what is clickbait? You just, what do you have? You're fishing, right? You just throw it out there and you won't believe what happens next. This is a clickbait, right? So you just want to click it to know what happens next. And this is bait. You don't need to click it. So how do we fight with that? We actually have a lot of moderators that look through random pages and annotate whether it's clickbait or not. We also have different classifiers based on neural networks, of course, that classify whether that is a clickbait or not. And we try to filter out those candidates from this pipeline so that it doesn't, give you like the best clickbait from the internet, right? This is one point. Another point is that we don't actually train here like a simple thing like log loss or anything like that. We actually, if we go into more details, we use some, if that information comes from our service, we can measure the reading time. And that is the engagement metric that you have mentioned. So this information will surprise you, but people read clickbait down to the every word. So we thought that, okay, so if we take like the most like readable material, what is that? It is still clickbait. I don't get it. So I thought that some meaningful like pages might be there, right? But there is a lot of clickbait there as well. So people are willing to read that clickbait, and I don't know what to do with that. Yeah. but we still use that signal to train a different DSSM. Yeah. So I guess that's pretty much it. Thank you again for having me.